give the feedback this side.
Testing, we'll do. This is Jim Adams. I'm the Deputy Chief Technologist at NASA. And you have just been introduced three amazing people that have a license to drive on Mars. So hopefully, we have a video that introduces them that we'll share in a moment. But one of the things that we want you to know is about halfway through, we're going to be joined by the crowd that signed up to spend time with an astronaut. So at the end of the hour, anybody who may leave, but you also may stay and part of being an astronaut. So what we really like to do is be able to keep 50 seats on this side available for those that will be coming in a few minutes. So I think one of the things that I was going to do as you were coming in was to show this movie called The 7 Minutes of Terror, but I won't because it will just take too much time. So
didn't touch anything.
Terrifying. So what I thought I would just do is say NASA has been putting rovers on Mars since the early 2000s. It's an amazing way to explore the surface of Mars, and it requires a lot of effort and a lot of skill. And these people are here today to tell you about how they do that. This session isn't really about what's in the rover as much as how they go about driving the rover. I'm sure they're happy to entertain your questions, and that's mostly what this is really all about today. Once you land on the surface of
So here you can see we have about 14 to 15 degree slopes with bedrocks.
which is verification and validation of our system. So we're basically testing things here on Earth and making sure that everything works right. It's kind of like practice before we actually execute those things on Mars.
I'm Amanda Steffi, and my job here is to be an engineer on the mechanical wheel wear tire team, and I've been characterizing the damage on the wheels that are currently on Mars. So Curiosity has been seeing some rocks that are a little bit sharper and a little bit more cemented than what was anticipated. And so one of the things that we've been testing here is some of those types of rocks. And so that's really what's been going on very carefully in this 3-wheel test track here. So there's a section of small cemented rocks, and then there's a section of limestone with a different composition of the rocks, and then there's some sandier stuff with some smaller rocks as well, and then they have boards with larger rocks. And one of the tests that I was more involved with was taking one of the wheels that we had been testing on the vehicle system test bed and running it over this track right here, which you can see is a mixture of flagstones and then some large-ish sharper rocks to try and kind of give it the worst that we'll see and take it to failure. In the classroom, failure is often a bad thing, but here in Mars, with our testing, failure is a good thing, and we're trying to get to failure because then we can understand what is going on and make sure that the Mars wheels never really end up like this.
My name is Larissa Hines. I am a member of the Curiosity Surface Operations team. I'm currently training to be a rover planner on the surface. The rover planners are the part of the team that actually put together the commands that are going to go up to the space tracks for either driving or doing sampling operations, like if we want to drill into a rock or scoop up some soil. So they're the part of the team that actually gets to work with the scientists and work with the other engineers to develop those plans and get them ready to send to Curiosity.
I hope you enjoyed the insider's tour of the Mars here, the piece of Mars on it.
Right, let's just see if we can get the other screen back on. There we go. We have our 3 panelists over there out in the US. We have Vandi, Ashitey, and Jaime. Can you hear us?
Yeah.
Yes, they can. Wonderful. So we're going to be opening up the floor to questions. Are there any burning questions that you have? And I must just tell you that these 3 are not glorified remote control drivers. These are serious, serious drivers because, of course, when you are trying to communicate with a remote control device on another planet, it's quite a complicated process. So I'm sure that a lot of you are going to want to know how do they communicate with this device and ask other questions like what are they trying to find on this planet, etc. So who would like to ask the first question? Don't be shy. Don't be shy. You're not going to ask questions I am.
Hey,
I have lots of questions.
Steve?
Yeah, oh,
I've got
yes.
I've got an incentive.
You've got an incentive? Okay, you're going to get a collectible Mars Curiosity rover sticker from the mission. What is your question?
I just want to ask them what's your most memorable story throughout their training or throughout their driving on Mars that they started?
Okay, so I don't know if you heard the question, but what is your most memorable story through your interaction of driving Curiosity on Mars? Or any other rover for that matter?
Most memorable
Then is he just someone who's going to speak? Rock, paper, scissors. Okay?
I guess I can just mention one we had relatively recently with Curiosity. And when we discussed, as you saw in the video, we've had problems with the Curiosity wheels because we hadn't anticipated the rocks on Mars to be quite as sharp. They're sort of, this area has very unusual rocks, and they were so sharp that they started impacting our wheels. And at that point, we realized that instead of driving in rocky terrain, we wanted to go and choose an alternate path and go through sandy terrain. However, our detour toward that path was this big dune called Dingo Gap. And that was really interesting and memorable because it's sort of like we had to have Curiosity drive over a sand dune, which is something we typically try to avoid because sometimes the wheels will spin in place and it won't go anywhere. But we made it successfully up and over, and I think that was a really great moment for the team. So I think that was a very memorable drive.
So for me, the most memorable drive was an opportunity when we drove several kilometers to Victoria Crater. And be able to see this in an orbital image, and to get there and to be able to see the physical crater match what is in the orbital image was actually one of the most fascinating drives that I've done on Mars.
And actually, another one we love to mention is the first drive is always fascinating because you see these tracks appear out of nowhere because we've just landed on Mars. So these tracks literally feel like something dropped out of the sky, which it did, and are driving out from there. So that, I think, is always, first drive is always a very memorable drive.
Okay, well, I mean, it really is a fascinating exercise looking at this particular device moving across the planet. But before we get to the next question, we have to admit that to actually get Curiosity into Mars, we're talking a whole new ballgame here. You guys had to really think outside of the box. Obviously, Mars is a different atmosphere to Earth, and you wanted to try and get Curiosity onto Mars in a different way to other landers. Could you maybe talk us through a little bit on how you actually got Curiosity onto Mars? Because that really was an epic engineering feat. And then we'll open the floor to more questions on what Curiosity is actually doing on Mars.
Okay, I'll talk a little bit about this. So it sounds like you didn't get to see the 7 Minutes of Terror video, but that's a really great video about how we landed Curiosity on Mars. So you should definitely watch that on YouTube if you get a chance. But actually, so when we launched Curiosity in November of 2011, right after Thanksgiving, so we started off, we launched, and then we had a long cruise to Mars, and we didn't get to Mars until August 5th of 2012. So then when Curiosity lands, it takes, starting about 40 minutes was about when we started what we called the EDL phase. So that's when Curiosity starts preparing, software and all that stuff to do the landing. But it was really those last 7 minutes where all of the events that land Curiosity on Mars take place. So first we need to get rid of the cruise stage, so basically the cruise stage of the spacecraft that got us all the way to Mars. And then we have a parachute, a largest supersonic parachute that has ever flown, deploying to slow us down. And then if you saw, I don't know if you've ever seen any pictures of it, but we then had the descent stage also do powered descent, so it has all these thrusters. I like to call it Curiosity's like jetpack to slow us down even more, and then lower Curiosity down to touch down on its wheels on a sky crane. So its long bridle lengthens out from separating Curiosity from the descent stage to the jetpack, and she landed right on her wheels, basically ready to go. That's why Vandi was talking about the tracks that come from nowhere. It was basically where we touched down, and then, after the first drive, got to drive away. And so why that was called the 7 Minutes of Terror is because that time, basically Curiosity had already landed by the time we first got any data saying that it had landed. So there's basically nothing you can do because the one-way light time is so long from Earth to Mars that just the time that it takes us to talk to Mars and the time that it takes Curiosity to come back was actually longer than those 7 minutes that it took to actually do the landing. So that's why we call it the 7 Minutes of Terror, because we just sit there biting our nails hoping that everything goes right, and we can't do anything about it if not. It all has to happen autonomously. We play software on board.
So, Jamie, this is Jim Adams. I think if the audience wants to stay late, we will show the 7 Minutes of Terror for you guys to do.
That's the best way to understand what's going on. It's hard to kind of explain it anymore.
Okay, the 7 Minutes of Terror really is a fascinating video because it does give you a visual understanding of exactly how difficult the engineering feat was to get Curiosity to Mars. But I'm sure we've got some questions in the audience. So, yes, over here.
Yeah, I've got 3 questions actually.
Well, we're going to have to try one if we can, because we want to try to get.
Is it still intended that Curiosity will get to the top of Mount Sharp and then sail where from there afterwards?
Can I just ask that one? So is Curiosity still intended to reach Mount Sharp? And then what happens after that, if it is intended to go there?
Reaching Mount Sharp. Actually, with Curiosity, we are in the foothills of Mount Sharp. Mount Sharp is this mountain which has a very large extent, and we are in an area called Perham, which is sort of the beginning of the foothills of Mount Sharp, and we've been there for quite a while, since about last September, I think. And we are currently at a location called Garden City, and it's a beautiful outcrop. If you get a chance to see it, you can see it on the JPL website. Every single picture that Curiosity takes with all the various cameras is available online on our website. And so you'll be able to see Garden City where we're at. So we are working our way up through the layers of Mount Sharp, because sort of that's what's interesting to science, is to see the history, which is sort of in these layers as we work our way through them. So we are sort of on that journey.
Okay. Any questions? We look for students that have got questions. Come on. Yes.
If Curiosity had to break, or you wanted to update the hardware of it, how would you do so? Because you obviously can't go and build it there on Mars.
How do you remotely repair or upgrade the firmware on Curiosity?
So upgrading software.
Okay, so I think we're a little unsure if we're upgrading software, upgrading hardware. I thought I heard hardware, but probably
firmware.
Okay.
Firmware or software games.
So basically, during the whole cruise, launch and cruise, we do update our software on a fairly regular basis. And I think we're currently updating to R10.
We actually just updated to R12.
To R12.
And we also have the ability to patch it with small patches of,
So basically, the way you upgrade if you're a Windows user, you get your Windows update. The rover gets its update on a regular basis. Okay, so every few years, we want to add new features to the software or new capability to the software. We build a new one and we update it. Currently, we're on version 12. Okay, the next version is going to be 13, 14. So it's just like you update your software on your PC. We do the same with the rover.
Steve, I would also say that, just to be just totally obvious, if there's a hardware problem, that's not necessarily fixable. And so there's redundancy on board the rover. Some of the systems are redundant just in case. But as was pointed out earlier, we're really careful about where you take this thing, right? Because if you run into a rock, you might cut up the tire or the wheels and that sort of stuff. So very careful. The drivers are very careful with the hardware itself, because it's precious stuff.
I would assume that from a software point of view, you have to be careful because you are transmitting the software over a connection, and if it breaks or one packet isn't sent through, you could corrupt the software upgrade, and that could yield Curiosity useless. Is that correct?
No, actually, that's not. We have an ability to validate everything we uplink. Also, we have multiple banks on the rover, so we always have a version we know works when we're swapping over. And there is a whole protocol on the spacecraft as to if we swapped and that didn't work. It has a certain protocol that works a certain time that will go into we have actually 2 computers on board, a backup and a main computer. So there's the probability that that could happen, given all the various checks, is very, very low. And in terms of hardware, which you were just talking about, the previous rovers, A Spirit and Opportunity, they were meant to last 90 days, and they've now been on Mars for over 10 years. And so as you can imagine, hardware does degrade. And what we do is we adapt how we drive. For example, Opportunity's wheel is stuck in a certain position, which is not quite straight. And we've learned how to drive with that and compensate for that. And so that is how we adapt to hardware, because unfortunately we can't send yet a mechanic to Mars to fix them.
And sometimes
Sorry, Jaime. So just to follow up on what she was saying earlier, we had one of our rovers that we ended up having to drive in reverse. Isn't that right? As I recall, that was it Spirit or Opportunity? We had mechanical problems. These guys get extremely innovative with the hardware that they have, because they know that they're very valuable and we can get amazing science, continue to get amazing science, even if you're going to drive it backwards.
And then Jaime, you were saying something before we rudely interrupted you.
I was just going to say that Vandi mentioned, sorry, there's a bug liner, that Vandi mentioned that sometimes we work around the hardware issues with operational constraints or change the way we operate, but also the flight software updates that we were talking about. Sometimes you can find ways in flight software to work around hardware issues, and that's one of the reasons why we make those software updates.
Okay, all right. Any other questions? Let's see, we're looking for young students first before we ask the more senior members of the audience. Yes?
What are the wheels made of?
What are the wheels made of?
What are the wheels made of?
The flexures are taken.
Oh, and titanium.
So it's a combination of aluminum and titanium.
We have
Actually, there's
We
some
can grab some out of there.
Yeah.
They're in the back wall.
Yeah, we can show you which parts are which.
Okay, so we might be able to get to see the wheels.
Yes.
Okay, oh, that's very exciting being on a virtual tour. Okay, let's see any other questions. Let's see, have a look. Any more students? Then we'll give you a chance. Yeah, okay.
What are the chances of curiosity?
Okay, so what happens if Curiosity does run into trouble, falls over a ditch, something happens to the device, and then you can't communicate anymore?
So I think one thing you have to realize is we do have safety features on board. The rover can do autonomous drive using the cameras, and the behaviors that are programmed into the rover is that it's not going to do anything that is unsafe. The other thing is that we do have communication windows loaded onto the rover, that the rover, even if it goes into a safe mode, would wake up every hour or two and try to communicate with us. So it's just built in. So it just hibernates, gets up, communicates, sends a few bits, and then we'll be able to catch it at the right time and be able to do that. And we've had that on Spirit an opportunity several times where we have the rover in the safe mode, and we'll be able to find the window that the rover is up, then we can get in there and then actually put in the fix.
The other thing is that we have redundant methods to communicate with the rover. We can communicate to the rover direct from Earth to the X-band antenna, which is pointed at Earth. That's the HTA antenna, which is sitting behind me. And there's also a UHF antenna that the rover can communicate to the orbiters with, and we can actually send things to the orbiters to then be relayed to the rover, and then also the rover sends data back to Earth via the orbiter, just as an FYI. But there's redundant ways to communicate between Earth and Mars.
Okay, and now I see you do have a wheel there. How heavy is it?
Now, just for scale, you can see the wheel is bigger than my head. Oh, that's your scale.
But it's, you know, it's
that's not
you can put Jimmy's head, my head, and Vandi's head in, and it will still fit. So that's scale. So as you can see, in the wheel, we have tracks. These are made of titanium, and the wheel itself is made of aluminum. It's a very clever design. It's very light. At the same time, it's carrying a very heavy load.
And also, if you want to talk about the pattern here, which is the VO pattern.
So if you look here, we also have some specific patterns on the wheel. So the tracks do make unique forms in the soil, and then we can use that with our cameras to be able to localize the position of the wheel. In addition, this is also a Morse code, okay? So as you drive along Mars, this Morse code is basically spelling JPL along the tracks.
Very cool. Did you know that? I heard a rumor that Curiosity can tweet. Is that true?
Tweet.
Oh yeah, Curiosity. You can follow Curiosity on Twitter. She tweets. I think it's.
I think it's Mars Curiosity.
I think it's
Curiosity.
Mars Curiosity.
It's not sarcastic Rover. Good Rover.
It's on the JPL website, the Curiosity Twitter handle.
Yeah, and it'll say official NASA JPL Twitter.
So if any of you do have Twitter, you can track down Curiosity and tweet her and see what she has to say. Yes?
Mars Curiosity.
I wanted to ask how, if people can only go to Mars a very long time in the future. Is there a chance of getting a 3D printer and another little robot to do repairs before people get there?
I don't know if you heard that, but I want to just add a little extra to that. So your next mission, would it involve sending a rover to Mars with a 3D printer that could perhaps repair older rovers and possibly self-repair itself? Self-repair itself?
I think this is very, very interesting. It's very futuristic, and basically we have a program what we call the precursor mission. So before we send humans to Mars, we want to send robots up to Mars to do all the prep work, to build the habitats, to build the factories, to create oxygen, and all the other things that will support human infrastructure too, so that humans can arrive on Mars, and then when they arrive there, they can start working immediately, so they don't spend their time building infrastructure. And I think with the innovation of 3D printing, I think that's a great idea for precursor missions.
So you see, you've just given an idea, and NASA might use that. That's fantastic. All right, yes?
What is the main body of the rover?
What is the main body of Curiosity made out of? And how heavy is it?
Warm electronic parts.
Mostly
So
There's aluminum.
composite as well.
Yeah.
So it's a combination of aluminum and some composite material. But we'll find out more and then post it on the website, the detail. So when you talk about the body, you're talking about the warm electronics box, because we have to keep the electronics, the computer and everything very warm at a certain temperature, because the Martian temperature varies from almost minus 90 to plus 70 degrees Celsius. So we want to make sure that the electronics have a very consistent temperature. So this is what we call the warm electronics box. But we'll find out the answer and then post it on the website.
Okay, yeah. Mm-hmm. Does Curiosity really sing happy birthday to itself? Herself?
Actually, we once had the SAM instrument. We have a SAM instrument, which is the sample analysis on Mars instrument, that Curiosity carries in its belly. So with the huge robotic arm we have, we drill sample, and we process that sample. We actually pass it through civet and create a baby aspirin-sized little sample, and we put it into the SAM instrument. This instrument is fairly sophisticated. It can detect it actually has various cups. It has multiple carousels, and in these cups you put the sample, and then it heats it to a high temperature and studies the gases. But it actually produces certain tones, and apparently on the first anniversary of Curiosity's landing, Sam sang a happy birthday song to Curiosity, and I think you could probably find it somewhere on the web.
That is very, very cool. Now all of a sudden I want to ask lots of questions. Yes?
Curiosity does break down and it becomes untraceable. How long will it take me to have a
You see, we were so worried about Curiosity breaking down. How long will it take to send a replacement? Are you already planning your next replacement? And when is that replacement going to land on Mars?
So I think the way you want to talk about 8 to 10 years, actually come out the concept of Curiosity, go through the formulation phase, the development phase, and the launch, right? It does take a long time to build a Mars rover. So it's not done overnight, it does take time. And we don't usually, most of our systems are one of a kind. So the next mission will look a little bit like Curiosity in 2020, but will be slightly different. We always add to our existing designs. So I don't think we'll be flying another exact copy of it. We'll fly something that looks similar, but it will have some modifications to it.
They'll have different science
So Steve, if I could just try, of course. I'll just, the mic is dead, but I want the JPL to.
So I'll speak from a NASA headquarters standpoint, since they won't tell you. And that is that NASA is planning to fly the next rover to the surface of Mars in 2020. And I believe you guys are already working on it. So,
And it's going to be a cooperative experiment. It'll have experiments not only for science, but also for human spaceflight as well. It's going to have an instrument on board that will help us figure out if we can actually take the water we find on Mars and turn it into gases that we would need to make rocket fuel. And so that will be a very exciting experiment, and it'll start the process, like they were speaking about earlier, of determining whether or not we can send robots ahead of human beings to build up the infrastructure necessary to explore Mars with human beings.
Okay. Have a question over here? Yeah.
Yeah, from a teacher or an educator's point of view, I would like to know something more about the drivers. How did they do at school? What did they study, and what were their favorite subjects?
Okay, this is a very good question. From a teacher's point of view, they would like to know a little bit more background of each of you. What did you study at school, and what were your favorite subjects? And I'm hoping that you're going to say one that starts with M and ends with an S, but I'm not going to say which one it is. Would you like to tell us what did you study and what were your favorite subjects?
Sorry, mate, this was whether NASA considered ladies to be better drivers than.
And please throw in, do you consider the women to be better drivers than the men?
So, I guess we have lots of a mix of different people, and they all have different perspectives. So, gosh, we'd have to figure out who got us stuck more. But in terms of school, I loved math and science when I was in school, and I studied in my undergraduate is in electrical engineering. I have a master's in robotics and computer science, and a master's in computer science, and I have a doctorate in robotics. And my favorite subject was robotics.
Okay, so I went up to high school in Ghana, and I was very interested in science. I did my bachelor's at Queen Mary College, University of London, in aeronautics. Then I did my PhD at Cranfield in aeronautics, mostly for control systems. And I did my postdoc at Carnegie Mellon, where I applied control systems to robotics, and that's how I ended up at NASA working on robotics.
So I think in school, as a high school student, I did like math and science, but I liked a lot of different things, and it took me a while to figure out that engineering was right for me. I didn't know that was something that I was going to study, but when I graduated, I went to engineering school in the University of Colorado in Boulder, and my bachelor's is in aerospace engineering, and I'm currently getting my master's in mechanical engineering at the University of Southern California. So I work full-time and part-time go to school. And I commute to DPL actually in systems engineering, so I was doing the systems engineering, a lot of the testing for the entry, descent, landing, and then when we landed the surface sampling system, things on the end of the arm, and then that's how I ended up now training to be a rover driver.
Okay, so I think the common theme is obviously the maths, the science, and the engineering, and I think in any team you need to bring different disciplines through. I'm very pleased to see that we have someone from Africa as part of the team, and that also gives hope to many of our students over here. Maybe a few of you will be joining them for the next Mars launch in 8 to 10 years' time. You never know. All right, if someone who hasn't had a turn yet, yeah.
What sort of automated systems do they have for the driving? So using things like image processing and stuff like that to actually find sharp rocks and try and dodge that, or to stop before going off a cliff.
Okay, so the question is, what sort of mechanism do you use for your driving or automated driving? Is it using image processing? Or what was it? What else was there? Image processing. Is it using echolocation? What sort of techniques are you using to get Curiosity to autonomously drive around Mars?
So what we have on Curiosity, we actually do driving in various levels of autonomy. In some senses, Curiosity is always driving on her own because we do not remote control the rover because of the great time delay. But the level at which we control it can vary. Sometimes, where we would say, we would very carefully tell it, okay, go 10 meters here, then turn 10 degrees, spin your wheels like this, and then go in this direction. So we are literally planning the route in great detail and say, if you didn't get this far, then go an extra 5 meters. And because that is much faster our computers, because they have to be radiation hardened, tend to be relatively slow. Then we have full autonomy for driving. On the mast of Curiosity are cameras that are called stereo cameras, and it's a camera pair. So there's a left camera and a right camera. And sort of like your eye, when you're looking at an image to tell how far something is, Curiosity can get that measurement. It takes images with its cameras and then runs an algorithm to figure out where the obstacles are, where the rocks are, where there are features that it should have. Once it's got that map, it puts it in its global map, and then it picks a path through there, and then runs that path, and then repeats that process. So yeah, so it can it uses computer vision for the driving. You want to add something?
So I think the way you want to think about the way we interact with Curiosity is that it's what we call shared autonomy. The humans do what the humans can do best. We look at the images, we can see a clear path, we tell Curiosity, drive this path. Beyond what the humans can see, they ask the rover to take over. So we work in partnership with the rover.
Okay, you have to put a lot of trust into and hope it doesn't develop its own personality. We have a question over here. Yes? Does Curiosity use fuel? My guess is that there are no fill-up stations on Mars. So how do you get to power Curiosity, and are you going to run out of power?
So Curiosity, unlike NER and Phoenix lander and those rovers, Curiosity uses what we call the radioisotope thermal generator. And basically, you have a radioactive source, and the temperature difference between the atmosphere and that gives you a delta T. And that delta T is used to generate power. And Curiosity has a 120 watts radioisotope thermal generator, which is basically a light bulb in your kitchen or somewhere. And all these signs, all these magnificent signs, the hundreds, thousands of images, and all the spectra that we're collecting is just coming from the 120 watt source. Okay, so that's very, very, it's incredible technology. And you can imagine this technology being used in rural areas around the world. We don't need huge jams or anything, but just using 120 watts to power a whole science laboratory on Mars.
And then it uses that energy source to charge the batteries. And then when we're driving and using the arm and stuff, we're actually discharging batteries. So Curiosity does have batteries, and sometimes we do need to limit how much we're doing and let the rover sleep so that we can charge up those batteries again. RTG.
It's quite a complicated process. Let's see. Yes.
To follow up on that, is there a redundant power source? So if something happened to the radioisotope generator, you have a secondary power source.
Do you have a redundant backup system, perhaps solar power, or something that would be there in case the isotope stops firing or just decides to die?
There's no backup with the radioisotope thermal generator. There are redundancies in other parts of the power system.
You see how worried we are about Curiosity? There's a general theme here, a lot of concern. Yes?
What's the top speed?
What is the top speed? Would you use Curiosity to race across Mars?
Not a race car.
Yeah.
What is
so Curiosity travels at 5 seconds. That's top speed.
We didn't get it. Can you repeat that?
A lot faster than we definitely walk the distance.
We didn't get. There was a slight delay there.
So Curiosity travels at 4 meters per second.
4 meters per second.
4 centimeters.
Centimeters. 4 centimeters per second. I've seen a few cars in Grahamstown moving at that speed as well. Wow. Okay, I can see that there are 50 Mars rovers in training. Let's have a look. Have you asked a question yet? Yeah.
Why not use solar energy?
Why aren't you using solar energy?
So if you look at the landings that we've done on Mars, usually we land around the equatorial region of Mars. And as you know, the sun, we're using solar power. I think when we started Curiosity, we wanted to go a little bit north. So as you go north, you want to go 30 something degrees latitude. Yeah, you wanted to go a little bit north. Using the radioisotope thermal generator gives you the option of being able to go outside the equatorial region, be able to travel very far, so you're not limited by solar power, right? Solar energy. So like Curiosity, if you look at Spirit, they have to be in the equatorial region, they cannot go further north, because as you get into the winter, you will have problems with power, because the sun will be in the southern hemisphere of Mars.
Okay. Before we ask the next question, one thing we need to know is
create an opportunity. When it gets to winter, we have to stop, park these rovers about 20 degrees south, so that they can survive the winter on Mars.
And also we got lucky with the wind clearing the solar panels. There's a lot of dust on Mars. If you look at any of the pictures, or any of our rovers, Mars is a very dusty place. And we will often clean dust rods and just even a week later, they are covered by dust. And so one of the problems you have with solar panels is if you're covered with dust, the amount of power you have decreases. And we were very lucky with the Mars exploration rovers because windstorms, like dust storms, just cleaned off those panels. But that's sort of something where you are depending on the climate and the weather, to just come around and do that for you. If you have a much longer time mission, you want a more reliable source.
Okay. That was a very comprehensive answer. The one thing you want to know is, of course, what is the most significant thing that Curiosity has discovered? I mean, you've sent this thing halfway around the universe to land, or maybe not halfway around, but you know what I mean, and landed on Mars, and now it's obviously looking for stuff. What is the most significant thing that it has found? You obviously can't tell us, it's top secret.
No, so I think that you have to understand the direction of the mission is to find out whether Mars has been habitable. In the past, basically what it boils down to is, can Mars support life? Has Mars been able to support life in the past and support life in the present? I think opportunity to answer the question around Gale crater that in the past could have supported life. Want to add anything to that?
Right, and actually one of the most interesting things we found was when we landed, the scientists discovered that there was this fan-like formation that was coming down from the edge of the crater into the floor. And even though we were heading sharp, we made a detour to go to Yellowknife Bay. And in Yellowknife Bay, we found all the ingredients. So that there was water, and they were the basic. We studied them with our various instruments, and we also drilled there. And so after that, we believe that Mars is a place that could have supported life. So that, I think, is one of the biggest discoveries that we trust.
The thing I would just echo, you guys, basically, if there was standing water there, I mean, Mars is very bad. I mean, we've seen with past rovers, obviously other signs that water had been there, and so we kind of knew that, but I mean, this was just basically a lake bed in the past, and there's a lot more that we're going to find out. I mean, we're just at the beginning, at the kind of bottom layers of Mount Sharp. It's this layered feature, and so as we go and we continue to explore all those layers, I think we're going to find out more things about Mars past, and so it's going to turn out done, and we're super exciting.
Okay. Apparently we've got time for two questions. Who hasn't had a turn to ask a question? Yes?
What type of motors or engines does Curiosity use?
What type of motors or engines does Curiosity use?
Curiosity uses various different, are you saying motors? That's what I heard. What types of motors it uses? Types of motors. Because it has very So it has a much higher average motors, about 2.5 motors for the wheels and for the robotic arm, for the main motors of the robotic arm. If there are different motors than we use on the Mir rovers, these are actually branching motors. And we have smaller motors, some 5-amp motors that we use for different parts of the arm. We also use even smaller motors to open the covers, the things that have to do very limited work, such as just opening the covers through which we provide sample into the instruments. We also have steering motors on the wheels, And in addition, some of the instruments have their own motors, such as to open the MOLLE cover and to spin the carousel inside the stand. So there is a huge variation of them that we have. That's the question.
Okay. Yes.
How far had the rover traveled since it arrived to Mars?
Okay, what is the total distance that Curiosity has covered, since we know that she only moves at 4 centimeters a minute? What is the total distance per second? Sorry, that was much faster than I anticipated. What is the total distance that she's covered so far?
Right. So Curiosity's mission was very different. It was not a rover trying to just cover distance. It's a laboratory. And the main huge accomplishment of Curiosity is to be able to collect samples, put them in the instruments and study them. And we have so many of them, like carrying around the laboratory. It has covered about 9.8 kilometers or so on Mars right now. And a lot of it is the fact whether we, for example, we can sometimes be at the same location for months if it's so interesting that the science team finds various things they want to study. Our previous rovers, for example, the Opportunity rover is about to complete a Mars marathon, which is the first Mars marathon that the rover would ever have completed. So that's the distance that it has covered in the 10 years last spent on Mars.
Okay, I'm going to hand over to Jim for closing remarks. Thank you very much to our panelists, but I'll let Jim say thank you as well.
Thank you, panelists. Thank you, JPL. Some of NASA's most innovative stuff. So the other thing you should know that is that it's roughly 9 or 10 o'clock on a Saturday morning at Jet Propulsion Lab, and these people normally have weekends off. Right? We didn't even get into when do you drive and when what do you do with your personal lives and how long is a Mars day and all those sorts of things. Those would be things that I'd encourage you to research on the internet. But thank you very much for coming in on a Saturday morning to talk with South Africa's biggest science festival, Scifest Africa. Thank you very much. So I think we're going to drop the Google Hangout link. And the next session that we have is Meet an Astronaut, Katie Coleman, who is an astronaut who's been to space 3